All right, so Newton came up with three laws of motion. Okay, we're going to go over all three, but today's lesson we're just going to talk about the first one. And Newton actually didn't come up with the first one entirely on his own. If we go back in time, like a long time ago, we had Aristotle. Aristotle came up with the idea that a force is required to maintain motion. And it's a very reasonable idea. If you take something heavy and you push it, when you stop pushing it, it stops moving. So it's not a bad idea to assume that, yes, motion requires a force. However, later Galileo started to do some experiments. This is much, much later. Galileo started to do some experiments with ramps. And what he tried to do was to remove friction, but you can't remove friction. So he did what we called thought experiments. And his thought experiments went like this. He had a ball rolling down an incline. And would go on a flat surface and then up an incline, like a half pipe. So a ball on a half pipe that would go like this. And he started to assume, well, if there is no friction, then it should come up back to the same height. And it would keep going back and forth, always coming up, always trying to get to the same height. So, what would happen if this wasn't a perfectly symmetrical half pipe? What if it looked like this? Well, in this case, the ball would travel further because it's still trying to get to that same height. Once it got to that same height, it would stop and roll back. Well, what if you didn't allow it to reach the same height? What if this pipe sort of had the ball roll down, but then continued to roll on a flat surface? Well, that ball's always going to try and reach that same height. It just never will, meaning it will always maintain motion. So Galileo thought, you don't need force to maintain motion. You need it to change motion. And Newton took this idea and put it into his first law of motion. Now, even though it was Galileo's idea, Newton coined the term inertia. He said inertia is a property of matter that causes any object to resist any change in its motion. So if you have something at rest, it wants to stay at rest. If you have something moving with a constant velocity, it wants to continue moving at a constant velocity. And it will do so until acted upon by an external net force. So there's lots of examples of this. Take a car, for example. If you're driving in your car is going at 100 kilometers per hour. You as well are moving at 100 kilometers per hour. If an external force is applied onto your car, maybe it hits something, that external force will bring it to a stop. But because Newton's first law holds, because you have also a certain inertia, you will continue moving at 100 kilometers per hour. And so that poses an engineering problem. How are we going to get the passenger to stop? Well, an external force has to apply on the passenger. If we do nothing, that external force will be provided by the windshield. That's obviously not what we want, right? That's extremely dangerous. So we design other things like seat belts, airbags, right? Other things to slowly bring the passenger to a safe stop. Other external forces. Okay, it's the same with a headrest. Right? If you're sitting at a red light and then you get rear-ended, your car gets pushed forward. Well, if your car gets pushed forward, your inertia wants to keep you at rest. But because you're sitting in a seat, the seat pushes you forward. But if there's no headrest, or if your headrest is not adjusted properly, if it's too low, your head will stay where it was and go back. I shouldn't say go back, it stays back. as the rest of your body moves forward. And that causes whiplash. Right? So you need that headrest to provide that external force to change your motion, right? And prevent injury. This is also famous like magic trick, right? But most magic tricks are just, well, I should say all magic is just science that we don't quite understand. Right? So in this case, the tablecloth pull, right? It's a very, very common magic trick. You have a dining set on a table with a tablecloth underneath, and you pull the tablecloth out without disturbing the dining set. Well, the dining set has inertia. It wants to maintain its state of rest, right? Unless acted upon by an external net force. So what your goal is to minimize the amount and the time that that external net force provides onto the dining set. So you're going to pull it out horizontally. You're not going to pull it out upwards because that's a large external force launching everything on the table. And you're going to pull it out horizontally as fast as you can. Because even pulling it out horizontally, there's going to be some frictional forces that will act. Right? So you need to minimize the time that they act on, just so that the position only shifts slightly. Right? And it'll work because those objects want to maintain their state of rest due to their own inertia. So I'm just going to pause here, and I'm going to show you a little. Right? So there's lots of other examples of inertia. Right? This is a simple one you can do at home. Right? You just take a cup. Right? You can put maybe something rigid, like a piece of cardboard, maybe cut it out from a package you received, put it on top of the cup, and then put a quarter in the middle. And if you flick off the cardboard, the quarter will just drop. It doesn't move with the cardboard because it wanted to maintain its state of motion, in this case, at rest. Right? So the cardboard moves out from under it. And then, of course, at that point, gravity is acting. Well, gravity was always acting, but there's a net force acting on the coin at this point, which is gravity, and it falls straight down into the cup. So that's something you can easily try at home. Another example is if you've ever had to push a car, right? It's easier to push it once you get it moving. Because once it's moving, it wants to stay moving. Right? Its inertia wants to keep it moving. So it's easier to actually keep it moving in that case. Right? So this was Newton's first law of motion, which is otherwise known as the law of inertia. Okay, there's just lots of other examples we can go over, which I have talked about. Okay, I've mentioned this also in the previous lesson, is even if there's an external force acting on the object, it still might not change its state of motion, because you can have multiple forces in opposite directions that add to a net force of 0. Right? And our examples, we had objects at rest, right? Like this example here, you have an object at rest with 2 people pushing on either side with the exact same force. But rest and motion really are relative terms, right? If this whole, if they're on a floor, which is one of those moving floors at the airport, not an escalator, but one that just goes horizontally, if they're on that and they're both pushing from either side, well, if you're just standing at the side, from your point of view, it's moving. But it's moving with a constant velocity. And that's the important thing. Inertia doesn't mean objects at rest want to stay at rest. It does, but it also means objects moving with a constant velocity want to maintain that constant velocity. So inertia is a property that resists change in motion. I've emphasized that a lot today. Change in motion, that change. is the important factor. Okay, I talked about headrests. Another thing is seatbelts. So how do seatbelts actually work? I mean, of course they work, they stop you. But I mean, you've probably played with seatbelts before. You can like pull them out, pull them in, right? But when you accelerate, they lock in place. Why do they lock in place? Well, this is what it looks like. Okay, here's your seatbelt attached to this sort of toothed gear, right? And below you have a pendulum, and that pendulum is just hanging. Now, you probably have seen this if you have something hanging from your rear view mirror. When you come into it, when you hit the brakes and stop quickly, it sort of swings. Well, that's what the pendulum's going to do. It'll swing, and when it swings, it locks into this tooth gear and suddenly stops it from spinning, and your seatbelt locks in place. Right? And the reason your objects swing forward is because they were moving forward. They were always moving forward. It's your car that came to a stop. Your car comes to a stop, but whatever you had hanging there didn't want to. It wanted to keep going forward, so it swings forward. So seatbelts themselves work based on Newton's first law, the principle of inertia. Okay, so I'm going to show you a couple other videos, but that's pretty much it for this lesson. We don't have any math problems, and tomorrow we'll do Newton's second law and third.